Hi everyone, mechanics. Today's lesson is the resisted vertical motion, lesson 1. Alright, when a particle is moving vertically, ups or downs, this acceleration due to gravity is always towards Earth. So that going straight down, mg, that's the force. Okay. So let's have a look at that. So force equals ma, and we know that from Newton's law number 2. If it's moving upwards, and then we normally say direction of motion is the positive direction, and then obviously opposite direction will be the negative. Now mg is always down, whether it doesn't really matter, direction of motion is upwards or downwards. Okay, so and then resistance force is always opposite to the direction of motion. Okay, if it's going up, it's down. It's down, it's up. Okay, and that will be expressed in a force form. It's F equals minus mg, because it's negative, minus R, the resistance force. And here, if its direction of motion is down, like a falling object, and that would be positive, that's positive now, and the resistance is negative. So that would be F equals mg minus R. Now we know F is ma, mg there, and R is depends on the linear or quadratic. So that's difference there. Okay, so let's have a look. Now terminal velocity is a free falling particle will eventually reach constant velocity by the air resistance or the resistance of the medium. So eventually, and that will actually prevent further acceleration, which is a equals 0, because it can't go any faster. So for example, if it's a falling object, it's going, like, you know, the velocity will increase as it falls, right? But then eventually, at some point, it'll stop increasing. Okay, so the velocity increases, and at some point it becomes constant, so it becomes steady. That means a constant speed. That means no acceleration, so no net force. Okay, so that's what happens. Next, and so therefore the free falling particle forces, there's no surface such, it just falls. So therefore no normal force, because normal force is what? Perpendicular to the surface, isn't it? Straight up. But air resistance is working like normal force. Okay, so air is like, think of it as air as a surface. Okay, so let's go through the question. Question 1 is there's 3 parts in there. A particle falls from rest. Now, I just already underlined it and I indicated myself. That means time is 0 and velocity is 0. Unless they actually tells you there's something different. And the retardation due to the air resistance is 0.8 v square meter per second squared. Now, retardation means what? Negative acceleration. So this whole thing, this is the acceleration, isn't it? So it is air resistance, R equals, it needs to be ma here, because it's in the acceleration units. So this is acceleration, okay? So you need to times by mass as well. So it becomes 0.8 mv squared, but it's going to be negative because it's a retardation is happening there. All right, so there's gravity equals 9.8 meter per second square to show that V equals 7 over 2 brackets, the expression there. And then show that the displacement, the distance, is this, and find the terminal velocity of the object. Now, when you say the terminal velocity, you need to think about 2 ways, because it's velocity is a constant. So time is moving, increasing, moving, you know, past, and so go to infinity, or acceleration is 0. So you got 2 ways of doing something like that. Okay, all right, so let's have a look at the part A. So it's a falling, Okay, so we're going to make the downwards as a positive, and then therefore the my mg force, the weight force, is positive, resistance force is negative. Okay, but I just put the minus 0.8 mv squared because that wasn't actually force, it was the acceleration, so I need to put mass there as well. So F equals mg minus r, because that's positive, that's negative, and then I'll put it into the ma and the mg and minus 0.8 mv squared. And obviously I want to get rid of the m because, you know, the less the better on this. And then of course the gravity is 9.8, so I'm going to put that in. Now this is only because I didn't want to have decimal. So to get rid of the decimal, you divide it by 10 with the actually integer number. So 98 minus 8 v squared all over 10, which I can simplify as 49 minus 4v squared over 5. Okay, now we need to make the v the subject because in the question it says that's how we have to prove it. Okay, so most of questions you will make it to a equals something and go from there, right? Depends on the equation is in terms of v in terms of t, or v in terms of x, or x. Whatever it is, I think it's the best way to go about is the acceleration equals first. So then you will have a couple of options to start with. Anyway, so we need to make the v the subject. So I'm going to use the dv dt equals that 49 minus 4v squared over 5. So now what I'm going to do here is I'm going to swap, because obviously to make the v the subject from here, we need to do integration, right? So we need to make it into as a comfortable form as a possible for integration, yes? So what I'm going to do here is I'll just swap this around. So that becomes dt over 5 equals dv over 49 minus 4v squared. Okay, so that's how I did it. And what happens now is integrate. So what I'm going to do here is I'm taking 1 over 5 out and integrate dt. Now here we can't just integrate. If it was a plus, then we can do inverse 10 and, you know, got some sort of thing we can work with. But it's obviously this one is partial fractions. So I factorize this because this is the difference of two squares, and then I put that into partial fraction form, and I'm trying to find the a and b, which is 1 over 14. Okay, so I'm going to take the 1 over 14 as my common constant there, and then put that into the partial fraction form there. So 1 over 14 out, and I need to, it's ln obviously, so I need to have derivative of 2v, which is 2, so I put the half out, and here is negative 2, so I'm going to take negative half out. So I'm taking the half out into the times by 1 over 14, so it'll be 1 over 28, and if I integrate, I will get ln 7 plus 2v minus ln 7 minus 2v. Okay, so I already integrate this one on the left hand side, which is 1 over 5t plus constant. You can have a constant this side or that side, doesn't really matter, but it's easier on this one. And 1 over 28th ln, because this is negative, you can write it in a fraction, which is the division, yeah. And then, initially the t equals 0, v equals 0, so we need to use that to find the constant, and constant equals 0. So therefore your overall equation is 1 over 5 t equals 1 over 28 ln 7 plus 2v over 7 minus 2v, and I just times by 28 because I want to make the whole thing, because the v has to be subject, yeah. So I'm going to get rid of the 1 over 28, so I times by that, and then obviously I want to make this as a normal as possible, so take e, and that will becomes 7 over 2v over 7 minus 2v, but then on this side it's the exponential, and I just changed 28 over 5 to 5.6t, just easier. and then times by 7 minus 2v on both sides, and obviously this is just normal algebra right now. And then I need to, collecting like terms really, because we want a v to be the subject, so we want the v to be on the left hand side altogether. And then happen to be that 7 is our common factor on the right hand side, and therefore that's what is required. Okay, so that's what the actual proof. Okay, so let's have a look at the B, part B. From A, we got this result. That V can be written as a dx over dt, because question part B was proving x equals something, right? So therefore I need to make it x the subject. To have that, V need to be dx dt. They're same anyway. So if I do that, now this is interesting part, what happened here. I need to integrate, right? We have to integrate. So you sort of predicted that integration will come because we want to make the x the subject. Only way we're going to do this is the integration. So to make a smooth integration, you want it, the derivative of the denominator to be on the numerator. Okay, now there is a way, maybe perhaps you could say, oh, what about using the constant changing instead of playing around with the exponential. But if you do that, it's going to be very complicated. So it's best you use the actual the t form there. So what I've done now is I swap this around, so it becomes negative here, okay, because I'm just times by negative here. And then what I've done is I'm trying to make this form the denominator, but still keep it into the original form. So when I do, the whole point of doing is I want to separate this, sort of like a partial fraction in a way. So I want to make a constant here, and then make this part as like a ln. That's my goal. Okay. So when I do that, I separate this, separate this. So that part becomes 1, because you cancel out on the top and the bottom, it will be 1. And this one will come like this. Now, in this side, I know the derivative of e to the power of 5.6t is actually 5.6 e to the power of 5.6t. So I can do this because I already got the right setting here. So I'm ready to do the integration. So if I do integrate the left-hand side, I will get the x that I want. And then I'm going to put it out the constant minus 7 over 2, integrate, and then the whole thing here. And I'll separate. So 1 is just t because it's a dt. And then I'll try to make the right condition here. I will take the 2 out, and I'll have to divide by 5.6 because I'm going to add the 5.6 on here. That'll give me a perfect ln form. So when I do that, I still have constant because we didn't have any limits. So constant will be when t equals 0, x is 0 because initially that's what happens. And then I'll get the my c, and I'll put it back into the original form with a c in it as a required. So that was the actual proof. Okay, so that wasn't too bad. Now, part C, finding a terminal velocity. There was a two-way of you can find the terminal velocity. Well, just say first one when t equals infinity, because that's how remember, terminal velocity, it starts with a constant velocity going down, 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 and when it reaches the certain point, which is when it's time actually passes, and they will just have a same constant velocity. And that means acceleration is 0. So I'm going to show you the two ways of doing this. So first one, from A, velocity was like this. It was a given, the proof. And then I'm just going to divide it by e to the power of 5.6t. Why? So here is the reason why I need to do that. Now, velocity, we want it to be constant. So we don't want to have this. We want to have a whole value. So I need to get rid of this, okay? So to make it 0. That's what I mean by get rid of it. So if t gets bigger, the whole thing is not going to be 0. Only way it's going to be 0 is in a fraction form, like 1 over this will be when t gets bigger. So that means 1 over the denominator gets bigger. That means whole thing will go towards 0. So if I could make it into fraction form, which is the e to the power of negative 5.6t, and then when t it goes infinity, that will go to 0. So to do that, you divide it by itself here. So if I do that, so I'm just dividing each term, and when I do that, it'll be 1 minus 1 over 1 plus 1 over. That means I can rewrite it like this. So I've got the negative power index right now. So when the t equals infinity, that's easy now, because that will go to 0. That will go to 0. So all I've got is v equals 7 over 2 meter per second, because that's a velocity. Or you can use a equals 0. So from a, part a equals 9.8 minus 0.8 v squared. We're going to make that equal 0 and make the v the subject. Now you will get the plus minus there, but we're going to pick 7 over 2 because it's a falling is positive. So that's a positive velocity we got. Okay, that's it. Well done.